All right, now we're going to introduce how to differentiate functions involving natural logarithm. Now, one thing that needs to be said before we move on is much like a trig function, that's not a multiplier. This is not natural log times, it's the natural log of. That's an outside expression. Also though, I would say before we get into the derivative rule for this, there are some algebra rewrites that we might be able to perform when we're going to integrate, or pardon me, when we're going to differentiate a logarithmic function. And those properties are on a slide that was uploaded to you called Logarithm Properties. Let's go through them quickly. All right, power property. And then these are the names I decided to give them. If we're taking the natural log of something to a power, this is an algebra property that says that power can be brought down in front. I would look here and go, no, that quantity doesn't have a power on it, so I guess that won't be applicable. But again, I would always go through, and we're going to do this on each one. We're going to see if we could use these properties to rewrite the thing first, because it does help a great deal. Product. Are we taking the natural log of a product? No, that's a single quantity inside there. It's not like this quantity is being multiplied by another quantity. If it was the natural log of two quantities being multiplied, product, then we could apply that idea. I don't see that happening on this one either. But again, check for these potential rewrites. And if they happen, great. And if they don't, oh well. It's going to happen on some of them that we'll enjoy later. And then the last one would be what I call the quotient property. If you're taking the natural log of a fraction, the rules of algebra say that's equal to the natural log of the numerator minus the natural log of the denominator. But again, this is not a fraction in here. So look for those potential rewrites. None of them happened here. They will on later ones though. So always check for that first. So I think we're ready to go. Now, I think the key question at this point becomes, I get it. This is going to be chain rule, because that's outside, that's inside. So wouldn't the first question here be, how do you take the derivative of the natural log of something? If you go back to Roman numeral 1, how do you take the derivative of a logarithmic, more specifically natural log? Well, if your function involves natural log, its derivative from the definition of derivative that we introduced a long time ago in chapter 3, wave your hands in the air. That turns out to be 1 over x. There's a proof of this. This involves the definition of derivative. Again, that would be a proof in a calculus book. So, natural log of something, 1 over something. So when you apply that idea to this, by the way, now we're finding derivative. So what's the derivative rule for natural log of something? 1 over that something. So this is the derivative rule associated with that operator. And then remember, according to the chain rule, then you do the derivative of what's inside. Remember how we take this times the internal operator, the internal expression. And in this case, you would just apply the power rule to those two terms. And this would be the derivative of what's inside. That's it, all right? So we're just plugging this new concept in. When the time comes, if the time comes, to take the derivative of natural log of something, it's 1 over that something. That's basically it. All right, let's practice a couple more of these. We'll do this column of examples here, and then we'll pause, and then we'll do the next column. That's it. All right, next example. Now, I hope by now we're accustomed to the idea that when we want to differentiate or perhaps integrate things involving radicals, that we would perform the rewrite. And so my very strong hope would be that you would change that cube root of 5x minus 7 into 5x minus 7 to the 1/3 power. That's an algebra rewrite we've been doing for a long time. And I hope that would be an instinct you would have on this particular one. So that's the first rewrite we would do on that. Okay, now, check to see if any of these logarithm properties would be applicable. Do we have the natural log of something to a power? Yes, we do. The natural log of something to a power. that power property, which is an algebra concept, notice there's no derivative being done yet. This is still f of x. But that property says if you're taking the natural log of something to a power, that power can be brought down in front and made into basically a coefficient. Come on down, power. Yes, and that takes a step out of the problem when we do the derivative. It makes it easier to differentiate this. So these are things that we would always want to look for. So I hope you all understand we applied that power property first. And we'll practice more of these until they become more and more second nature. And then, all right, now we're ready to find derivative. So f prime of x would be, that's just a coefficient, right? Just a number. So 1/3. And then, here we go with chain rule again. Outside, inside. So what's the derivative rule for natural log of something? 1 over that something. And that's the derivative rule that goes with this, 1 over. And then, according to the chain rule, the derivative of what's inside, which would just be 5 minus 0. So again, the 5 would be the derivative of what's inside. Boom. That could all be cleaned up a little bit. That's beside the point. Just demonstrate to me your understanding of how to find that derivative. To me, that's important. Don't worry about cleaning them up. So yeah, and it did help to pull that power down in front. And this is, again, an algebra concept as far as bringing that power down in front. We're taking advantage of algebra here. All right, let's do one more in this column and then we'll pause for a bit. Again, hit freeze if you need to. Okay, now, you get to where you can see these particular things. The natural log of cosine cubed of 4x. You know, in its present state, there's actually like 4 operators. Log, natural log, cosine, third power, 4x. That's a lot of layers. We could actually start chain ruling this thing out. But I would again always suggest to a person to investigate these ideas. One of the things you have to remember is that the cosine cubed of 4x is also the cosine of 4x quantity cubed. And my point in changing it like that is hopefully that would conjure up your idea, you know what, we're taking the natural log of something to a power. Because that third power is being applied to cosine 4x, isn't it? Whether it's in here or out here. So the point would be, before we get all calculus crazy, we would go, you know what, that 3 can be brought down in front. Because we effectively had the natural log of something to a power. And that power can be brought down in front. All right, another thing a person might think, product, but that cosine is not being multiplied with the 4x. So this isn't some sort of product in here. I think we're done with all the algebra rewrite that we can possibly do. And those are rules of algebra that we can use to our advantage. So now let's start taking the derivative. 3 is just a coefficient. And here we go, natural log and all that. And again, my hope would be chain rule jumps in your mind, whereby you would say, okay, this is outside. What's the derivative rule for natural log of something? 1 over that something. And this is what emerges from natural log of something when we differentiate. And then we do the inside. Chain rule. Oh, now what? We got outside cosine, inside 4x. So the derivative for cosine is negative sine. Leave the 4x alone. And then the derivative of the 4x would be the 4. So again, working our way inward, inward, inward. So the cosine of 4x gave us this. And then the 4x itself gave us this. Chain rule. Work our way from outside to inside. Operationally. So that's an idea we've had around for a while. And I just want to take a look at that slide again. I guess I could keep going, but I think let's just take a deep breath. We'll come back and do that other column of examples here. And we're punching our way along. All right.